In this video, we'll begin section 7.2, that is trigonometric integral. We'll try to use trig identity here to integrate certain combination of trigonometric functions. Before we begin, it is important we recall some basic trig identities that will be useful to us in this section of the class. Recall basically that from pre-calc, you've learned that sine squared of x plus cosine of squared of x is equal to 1. And from there, we can derive this identity by moving cosine to the right-hand side, or this identity by moving sine to the right-hand side. If we divide this through by cosine of x, we'll get this identity. Dividing this by cosine of x gives us this, by cosine of x gives us this, and this by cosine squared of x gives us this. Another way to write this is what we have at the right hand side. You may have also recalled the half angle formula given by this, and for sine and cosine. Also the double angle formula, you may have remembered this. So we'll be using these properties or identities while working in this section. We'll begin by considering integrals containing powers of sines and cosine, powers of tangent, and then we'll consider the ones that doesn't have power but maybe some kind of combination of sines and cosine. Let's start with an example and then formalize as we go forward. Now, suppose we are asked to integrate the cosine cubed of x dx. To do this, I'm going to write this, splitting this to have cosine squared of x multiplied by cosine squared. I just factored out one cosine here to get this. So I can write my cosine squared to be equal to 1 minus sine squared of x, cosine of x, and then the x. If I make the substitution, if I let my u to be equal to sine of x, this then means that my du is going to be equal to cosine of x dx. And then if I substitute that into my original integral, I'm going to have that cosine cubed dx will be equal to the integral of 1 minus sine squared is going to be u squared. And then cosine x dx is the same thing as du. Integrating this, if I integrate one, I'm going to get u minus u cubed over 3 plus a c. But my u was sine of x, so this is going to be like sine x minus sine cubed of x all over 3 plus constant c. It looks very much straightforward. Recall that we can also solve this using the trig or the reduction formula that we saw in the last section. Recall that for cosine, we saw that the integral of cosine of n to the power of x by reduction formula. In fact, I think it's better to change ink here. Or by reduction formula. We have that, probably write it above. Integral of cosine of n to the power of n dx is equal to 1 over n sine x cosine of n minus 1 x plus n minus 1 all over n integral of cosine of n minus 2 x dx. So if we apply that to integral of cosine cubed x dx, that's going to be, my n is 3, so I'll have like 1 over 3 sine x cosine of 3 minus 1 is going to be cosine squared, then minus n minus 1 is going to be 3 minus 1, which is 2 all over 3, and cosine of n minus 2 is 3 minus 2 is just going to be 1, so you just have cos x dx. That would be equal to 1/3 cosine of x sine squared of x minus, or this should be a plus here, please, plus 2 over 3. If we integrate cosine of x, we just get sine x plus c. Now, if you look at this, it doesn't really quite look like what we already have. But then we can actually rewrite this to be in this form by noting that we can write this as 1/3 cosine of x, or rather, I think this should be the other way here. I'm supposed to have sine x cosine squared x, right? So this is going to be 1/3 sine x. My cosine squared, I'm going to change it to 1 minus sine squared of x, and then plus 2 over 3 sine of x plus c. That would be 1/3. If I multiply this out, I'm going to get like 1/3 sine x alone minus sine times sine squared is going to be sine to the power of 3 all over 3, and then plus 2 over 3 sine x plus c. 1 over 3 sine x plus 2 over 3 sine x is just going to give me sine x. So at the end of the day, I have sine x, only sine x, then minus sine cubed of x all over 3, and then plus c, which is the same with what I got using substitution above. So any of the method should work. However, in this section, we are going to develop some strategy to compute integrals that involve powers of sine and cosine. In general, if we try to write the integral involving powers of sine and cosine in the form where we only have one sine factor and the remainder of the expression is in terms of cosine, or we only have one cosine factor and the remainder of the expression is in terms of sine. If we're able to do that, then we can use the identity that sine squared plus cosine squared is equal to 1, or the variant of that identity, to convert back or forth between powers of sine and cosine. In summary, we can say that the strategy for evaluating any integral of the form, here there should be an integral here, please, of the form integral of sine of ms cosine to the power of nx dx, where m and n are integers that are 0 or bigger than 0. First, if the power of cosine is odd, that means n can be written as 2k plus 1. This is the general form of an odd number. This k here is an integer, actually positive in this case. Then we can save one cosine factor and then use the identity that cosine squared is equal to 1 minus sine squared to express the remaining factor in terms of sine and then integrate. That is explained here. Instead of having this, if my n is odd, I can write n as 2k plus 1. And then 2k plus 1 here, I can split that into cosine to the power of 2k times cosine the x. And then at this point here, cosine to the power of 2k is the same thing as cosine squared to the power of k. And then I can split my cosine squared to be 1 minus sine squared. If you check here, everything is in terms of sine x except for the cosine of x. So if we make the substitution that u is equal to sine x, then when we differentiate u, we get cos s dx, so that this term here becomes my du, and then this is going to be like integral of u to the power of m multiplied by 1 minus u squared to the power of k, then du, and I can integrate this in terms of u. On the other hand, if the power of cosine is odd, or the power of sine this time is odd, this should be sine, please. If the power of sine is odd, that means we have here we have that m is equal to 2k plus 1. Then we want to save one sine factor. We want to save one sine factor and then use the expression that cosines, or probably this should have been the other way around. Use the expression that sine squared of x is equal to 1 minus cosine squared of x to express the remaining factor in terms of sine or cosine. So that is what was done here. Our m was odd. In that case, we could actually write it as, instead of m, we'll have 2k plus 1. At this point, we factor out 1 power of sine. This should be sine. I really don't know why this has too many errors. So factor 1 sine power out. Over here, we'll do the same thing. 2 sine to the power of 2k is something as sine squared, or to the power of k. And then we have 1 factor of sine. Cosine still remains the same, we are not touching it. And then we can change this factor to 1 minus cosine squared, and then to the power of k, so that we have this. So at the end of the day, when we make the substitution, u is equal to cosine of x, then my du is going to be negative sine x dx. That tells me that this integral here in terms of u is going to be, this negative would actually come outside. So I will have that my minus du will be equal to sine x dx. So I'll have this to be integral of negative 1 minus u squared to the power of k, u to the power of n, and then du. Sine x dx is negative du. So here my integral is now in terms of u, and I can now do the integration. It's possible that you could have both sine and cosine to have odd powers. If that is the case, you can either use this strategy A or the strategy B. Finally, if both powers are even, both powers of sine and cosine are even, then it is best if we use the either of the half angle formula. Sometimes we may want to use the double angle formula. Sine x times cosine x is equal to 1 multiplied by sine 2x. This should be 1/2 sine 2x. Sine of 2x. Okay, so at this point, we can look at some examples about this. As we look at the examples, see how we are able to apply these concepts given here. I think we may look at all the examples together in one video. We'll stop this at this point.